So let's continue. So by the way, like Piang is gone, so I hopefully I guess you are aware that we have homework, and then so if you have any questions, just email me. So let me get back to the material. So let me maybe start a new page here.
Homework you do at 20?
Yeah, I think it's due this Friday. Yes. So I kind of like give an example, just try to as an exercise of what we discussed so far with like some mutual information, entropy, and so on. This is actually from also like a Shannon's paper. This is the perfect secrecy. So the idea is a cryptography basically. So but it's in a pretty theoretical setting. So let's say we have something is a kind of personal that you don't want to let anyone to see except someone special that can able to read it. So we are going to first let's say encrypt the letter with some code and then decrypt the message back. So it's a classic kind of cryptography setup. So we have basically like some message that we are trying to decrypt, encrypt. So let's say the message we call it M. Then it will code into some ciphertext. So some ciphertext is basically something like just kind of code that people cannot see easily. And to encrypt that is going to use a key for the encryption. And then when you have the ciphertext, when you have the key, then supposedly you're able to decrypt the message back and decrypt the original message back. So here is we just talk about a Shannon's result. So Shannon's result here is saying that if you want to have perfect secrecy, then basically the size of your key is as big as your size of your message. So kind of a sad news here. For example, if I'm trying to encrypt something like a message I'm sending to someone else, I need to have some key to protect that message. My key will be at least as big as the message to make sure that the whole message is perfectly secret. And that's, in other words, I will have like the entropy of the message will be less than equal to the entropy of the key. This is the Shannon's result. We're going to prove that. We're going to prove these results here. So so here we first assume that like the whole kind of encryption and decryption process is deterministic. So therefore, like basically, if I'm looking at the entropy of the message given the key and the ciphertext, so what should this be? Yes.
The ciphertext is the ciphertext a message after message. Ciphertext after message.
The ciphertext is basically the encrypted message. This is actually the encrypted message. So you have the key. We are considering kind of a symmetric setup. Encrypt the message, something like. So you have the key, you encrypt the message into the ciphertext, and then you have to use the key to recover the message again back.
So what's the question?
What's the entropy, the conditional entropy of of M given KMC.
We should derive that first.
Yeah, I mean, like, you can say it out actually. What should be the entropy?
Same with the message.
Yes. I guess I should stop this. Yes, same. No. Given KMC. Yes.
KMC. Less than message itself. Less than entropy of message itself.
Let's see, like that's on the gut. Mona, are you still here? Like, do you want to answer the question? Or do you get the question? Oh wait, I cannot hear you actually somehow. Let's see, is that the volume is too low or? I see your mic is, but there's no. I think like yeah, your mic probably is not working because the green bar at your mic doesn't seems to. Oh, okay. I think it's okay. There's some. See, there's a click or something that. Oh, I can hear you now. Nice. Yes. Okay. Yeah. Yes. Actually, you may want to go closer to the mic. Yeah, it's very.
I think the answer of the question should be 0.
Yes. Okay. Great. So nice to hear your voice. So yes, this should be 0, right? Okay.
0.
Yes, because I know, right? Here we assume that like at the decoding, like you have the key and then you have the ciphertext. You recover the message losslessly, right? So given the key and the ciphertext, like there should be no uncertainty for the message, right? So therefore, like HM given case, it should be just simply 0. So and okay, let's have another. Also like let's make one assumption is that like let's assume like M and C should be independent. So for perfect secrecy, we're hoping that like you cannot basically M and C independent will be just I M C will be 0, right? So there will be no mutual information between one another. So and then in the sense there's no way you can extract any the real message, any piece of real message from the ciphertext alone. So then we basically have this two condition first, and then let's see. So since IMC is equal to 0, I have HM is equal to HM given Z plus ICM, let's say. So we have this because ICM is equal to HM minus HM given Z, right? And ICM is equal to 0, therefore it's just equal to HM given Z here. Now, and we claim that like HM given C is less than, actually this will be, this one is actually will be less than equal to HK given C. So because I have like HM given C is equal to, sorry, it's less than equal to HM K given C, right? It's just like, okay, this is very reasonable, right? Because HM K given C is just equal to HM given C plus HK given MC, right? So here we assume everything is discrete, so therefore like HK given MC is positive, therefore like I have HM K given C is like bigger than equal to HM given C. But this HMK given C is equal to HK given C plus HM given HM given KC, right? Just another way to writing it. But then like by this assumption here, not as actually not a really assumption, just a very reasonable kind of setup that like my message can be completely determined by the key and the ciphertext. This will be gone, this will be equal to 0. So therefore I have HK given C is bigger than equal to HM given C. So I have this one. Now but of course HK given C should be less than equal to HK, right? Because just conditioning will reduce its entropy, right?
Yeah.
Yeah. So knowing some information C will always like make the information.
Where is it come?
Which one?
Where is come from? I mean, where is in here? This is come in here.
Oh no. Wait. This one here is equal to this one, right?
Oh, that's
yeah. I just want to say because this one is equal to that, therefore like HMK given C is bigger than equal to HM given C here.
Okay. And this one?
And then I can expand it the other way, right? I can expand this way, and I can expand the other way. It will be HK given C, but HM given KC here.
Oh, okay. So
yeah.
At the above is not use any again. So just below.
Yes.
And
Yes.
then that's 0, and therefore
yes.
K given C.
Yeah.
And you come to there. To over there.
Yes.
Oh, okay.
So therefore like then you see we have basically HM is actually just equal to HM given C if we assume C and M to be independent, and then this one from here is less than equal to HK given C, and also conditioning reduces entropy, therefore HK is less than equal to HK, so therefore we have HM is less than equal to HK. Yeah. So it just says that like to have like perfect secrecy, So
in here we should send K bigger than M. That's intuitively something like that. We should send K bigger than M.
yeah, actually it's saying that like your K has to be bigger than M. Yeah, if you yeah, but in practice, of course, people don't do it, right? But in the sense that if you really need perfect secrecy, you see that the argument is basically from here, right? The perfect secrecy is saying that my key or this encryption process will break the dependency completely. So since I break the dependency completely, there's no way I can decipher the text without the key. So from the ciphertext alone, it's basically it's garbage. Like it does not depend on the message at all.
It depends on the side on the key.
It actually depends on. It's hard to say. Like basically, what we're using is just this one. Right? It's saying that if you give me the key and give me the ciphertext, I will be able to completely determine the message. And at the same time, we actually only use these two conditions. Right? This is very reasonable. This one is like you must have that way because I have the key, have the ciphertext. M has to be deterministic, right? Able to losslessly recover that. But this is more like I shouldn't say very strong, but like a perfect ideal situation that like if you don't want to have any kind of like security or like as like Shannon put it, like some perfect secrecy, then I just have to force the mutual information between the message and the ciphertext to be sealed, so that like given the ciphertext alone, there's no way we can recover the message.
Yeah.
But then like forcing that basically eventually need to like your message, actually or your key has to be at least the size of the message. So that's therefore you have to like kind of one-time pad. How they do is basically you have the key. Just a simple, for example, if it's a binary message, your key can be just another binary kind of sequence. You just add them together, right? You have the key as long as, have the same name as your message. And you add them together, and then you have something like the ciphertext is totally independent to the message. If your key and the message are independent to one another. But but in practice, of course, no one uses it. That is too much. Yeah. But that kind of interesting, I guess. So anyway, let me just give a summary in terms of all this information measure that we mentioned, like the mutual information. Let's say IXY. People like to kind of memorize the relationship of them using a Venn diagram. So basically, like for example, if I have this circle represent like HX here, let's say. Maybe I use several different colors, maybe better. Let's say this is HX, and let's say this is HY, right? Then basically this part here will be H X given Y, and what in the middle, let me use and look up. What in the middle will be the mutual information IXY, and on this side will be like H Y given X. So by the way, what's HXY here? HXY.
I think that IXY is
Actually,
This one is this one. This one. All of these minus this.
yes. No, you don't need to minus this. Actually, you're almost right. That's all of this is hxy because this is hxy is actually equal to hx plus hy
Yeah.
given x, right?
Yeah.
Hx is this one.
Mhm.
Hy given x is this one,
Yeah.
right? So therefore, this will be just hxy.
What is HX?
Hx is this one.
Oh yeah, that's right.
Yeah.
And
So
then-
hx and hy given x is this one here, right?
Yeah, that's right.
Or you can say like it's hy plus x given y, right?
Yeah. I mean that X. Can we write something like this also? Sx plus x
Hy
minus
ixy.
yeah.
Yes,
XY.
yes. Yeah, you have that equation also. You can prove that like actually it's very easy to show it. This is exactly it's hy
Yeah.
minus minus ixy, right?
Minus xy.
Because ixy is equal to hy minus hy given x, so hy given x is hy minus ixy. So as you said, like hxy is also hx plus hy minus ixy. And so this is a kind of, and of course you can add more, add the third variables here. Let's say I can put a z here. Then let's say this circle is a hz here. Then you can define, for example, like what's this part here?
That's x8 to x8 and minus a lot of things about that.
Yeah, that one is okay. Let's see. This one will be like I, x, and z, right? Because this guy here.
Mm-hmm.
Oh no, I guess this is probably not. This is
That's I.
how to avoid that. Let's see how to.
So minus by
This is a little bit more difficult first. Maybe I start with a simpler things first. How about this?
that's usually we have this that's yeah, we can write one by one. Dr. Chan.
Yes.
This one first minus this one xy, and then we find this one area, and after that minus with the hx. So we got this. That's chain.
Chain rule. I see.
One by one. Minus by hy, after that minus by hx, with plus by I, x, y, z, because we should have x, y, z inside there, in the middle. So
No, actually, it's not. But let me just give the answer for this one. This actually turns out this is just z given xy. So this region is hc given xy. And this part here, we already know this part is a hc given y, right?
Given y.
Yeah. It's like for this part here. It's like for this part here, it's like hx given y. So this part here is like hc given y. So therefore, if we back to our earlier question here, what is this here? This is basically hc given y minus hc given xy. And so this one is hc given y minus hc given xy. And this is actually I see x given y.
Oh yeah, that's right.
Yeah. So and by the way, like here we are talking about like discrete random variable. Let's focus on discrete random variable. All these are positive, like all hx, hy, xz, and also like mutual information is like assumed to be positive. And then like but you see here, this term here in the middle,
I, X, Y, Z.
you can call that way. Not all textbook at least define that. I saw like one textbook did, but it's not exactly like something like defined in every textbook. But this one, we see that this one is actually equal to this here is just like IXC, right? This one is, oops. Okay. Oops. I guess I'm out of battery, so I forgot to put it back. So this one is equal to IXC, right? IXC minus this one, right? IXC given y, right? I mean, or of course I can have other combination. It can be also for example, IXY minus IXY given Z.
IXZ given IXZ. So IXZ. X equal to Z. So tell me IXZ given Y, where's the area IXZ given Y?
Oh, IXZ given Y is this one here. IXZ given Y is here. Right. This one is IXZ given Y. So I say,
yeah, that's right. So something like given is mean that outside from that guy.
yeah, it's kind of like that. So, but if you look at this, okay, therefore, like this part is actually is IC minus IC given Y. So, but then now you remember like what we mentioned last time. I mean, not last time, like just earlier. IC will be equal to 0 if like x is independent of C, right?
Yeah, that's right.
And IC given Y will be equal to 0 if like x is in C given Y, right?
Given Y, yeah, that's right.
And basically we can find situation that like x and c are independent, but like x and c are not conditionally independent given y, right? So therefore like this actually in general can be positive or negative, can be like bigger than less than you. So therefore like this figure is actually a bit misleading. Like everything is like kind of correct if you think of like every area here is like positive, kind of like can have like a positive area, except this place here. Be very careful. Like this place here that oftentimes the textbook won't define. It can be either positive or negative. Yeah.
Because why negative?
Oh, because why negative?
Mm-hmm.
As I said, like because this part here is actually equal to this way.
Yeah, that's right.
But then I can find cases like this part is bigger than 0, but this is equal to 0. Basically, I can find x and c are not conditionally independent given y, but x and c itself are independent to each other themselves. For example, like we have that coin example again, like we flip coin, like the two outcome is basically x and c, and y is basically is equal to x plus c. Then in this case, x and c are not conditionally independent given y, right?
Yeah.
But x and c are independent to one another. Yeah. So therefore, like this can be, yeah. So
can be negative or positive.
yeah. So yeah. But this figure is kind of nice to memorize all this, but just be very careful for the central area here. This does not necessary to be 0. So let's see.
There's only on 3 variable. If on the
Yeah.
3 variable is always more than 0.
Yeah.
Greater than 0.
It'll be always positive.
It will be always positive. But 3, 4, 5 is will be can be.
Yeah. 3 is like that. 4 probably is. Yeah. 4 definitely is because you can combine two variables. Think of like just yeah. Sorry. Okay, maybe. This is a kind of summary of all this. So what next is I'm going to talk about a toy example. Let's see if I can. This is 68. Let's see. Oh, wait a sec. I have slides here, right? I don't need to. I forgot. Guess I will just copy this. So this is a kind of a example from I think it's an AI class from MIT, I guess. So it's a kind of an example for decision tree, but I find that like we can also explain this with kind of some mutual kind of like information theory kind of like terminology to explain that. So it's kind of nice to kind of discuss here. So let me again just create a new this is some of the, I think hopefully you guys can see it, but maybe I just put it here. So I'll come back to this every once in a while for convenience. So here just a very kind of dummy toy example that like we're trying to let's say trying to recognize a vampire and there's some kind of characteristics of a vampire, so it's a classification problem. Like for example, like some characteristic like whether the vampire has a shadow or no shadows, and whether it's afraid of garlic or not, or like what kind of complexion like his skin has, like his pale, wealthy, average, and so on, and then like whether he has an accent, is a strong accent, like an off accent, basically all accent and heavy accent.
What is Rudy in there?
Huh?
Rudy.
I guess it's a kind of red. I guess I'm not quite sure actually. Yeah. So
Red.
I need to check the dictionary, but yeah, I assume so. I didn't. But anyway, I just call it R anyway, some feature. And now that given this, we're trying to classify. This may be our initial data. Use that to train some model to classify a vampire from not a vampire, right? So one way to do it is I just build a tree, right? So we have all these characteristics. Then the question is like, what characteristic is good to use, right? For example, like if you look at based on like the shadow characteristic shadow. So out of the shadow characteristics, and we have like examples here. We have like
No shadow.
no shadows. I have shadows. I'm also like don't know, cannot not clear or something. And then like for those I have yes with shadow, like all the result is negative, let's say. And I have like which one? I have with shadow, like
No.
this one have shadow, this one with shadow. That's what I mean, like for those like with shadows, all of them like it's not vampire. So like I have negative result here. I have 3 negative results here. And for one guy I have a shadow, for one guy I have no shadow, then it's identified as vampire. Then I have 1 positive result here. Okay. And then for the question mark, I have this one here is a negative result, this is a positive, negative. So I have basically 2 negative results and 2 positive results. This is like based on shadow alone. And I can do something similar, let's say, for whether like use the garlic test that like okay whether like it is afraid of garlic or like it doesn't care about garlic. And so for yes, that's a what that's a all negative. So I have like 3 negative here.
1, 2, 3.
Yeah. Have to draw.
3, 4, 5.
And for no garlic here, like I have like 3 yes and 2 no.
Yes.
Something like that. So I can try to draw similar trees for like each of the tests here. So the question is like, okay, which one we will pick? Let's say we just pick 1 characteristics to design. Okay, whether so the strategy here is like we will design a simple classification algorithm by looking at one characteristic at a time. For example, okay, we look at the shadow kind of characteristic, and based on that, we design whether it's likely to be a vampire or not. And after the test, maybe like there's some cases we cannot determine that, then we go for another test and another test and so on. And for example, like for the shadow test, if we trust all this data here, then we can say, okay, as long as it's half shadow, it will be negative. Then I will just stop there. We don't need to have more tests. But if after the shadow test, let's say the outcome is like this question mark here, we just need to have more tests. For example, like here, maybe here we go for a garlic test here, maybe, and then I just bench out again, and then I make the decision. In the garlic test, if it's yes, then maybe we are done. Let's say we trust this data here. Everyone have being like this is yes, okay. I'm thinking like that doesn't care about garlic, like it's kind of not a vampire, then we were just done here. But if the result is no, then we cannot stop here, then maybe we need to have more tests again, and so on and so forth. So then the question is like, which test we should go first? Something like, right? And of course, like okay, what do you suggest? I should just pause here.
Shadow first, negative.
But what should be a good rule of thumb? Like, I mean, like we have like several tests here. How can we say like one test is better than the other?
Find the probability, the success probability of the test.
Can you elaborate that? Like,
yeah, we can calculate the probability success that's found here or not found here by using for every step put.
But okay, the success is okay. So for example, this one, what's the probability of success for the shadow test?
For shadow test, for the no, there is 1, and for the yes is 3. So it means that for yes there is 3 per 1, 2, 3, 4, 5, 6, 7, 8. So 3 per 8, 3 over 8, and for no 1 over 8.
So then you say this would be like kind of 4 over 8?
Yeah, for yes, 3 over 8.
Yes.
So we can put the 3 over 8 in the yes and the no, and then we can calculate for with the below for every step.
Yes, it's kind of true. So
this one, and then we calculate all of the probability.
yes, so in a sense, like what you're saying is like we will look for the test that can like that can identify for sure from the data that like the whether like it's a vampire or not. In the sense like it can completely separate the data. That like have for example after the outcome, basically like for this outcome it basically completely separate whether it's a vampire or not. Will determine whether it's a vampire or not.
Mm.
But the problem here is like here we have a small test size, right? Small data size, right? But if we have lots of training data, you expect that like this one. I mean, we won't have like any of this outcome can be completely differentiate is a vampire or not, right? That's if this is not just 3 outcomes, we have like 1,000 outcomes. There will be like always some exceptions, right? We may have like 1, 2 exceptions there, right? Then in that case, like that one was the how do you say like? Then in that case, like for all these, the accuracy won't be.
That would be.
Yeah, this one, for example, like for this one, you can say, okay, this one I can completely identify as a vampire, so I can't that like I can out of 8 of them I can completely separate vampires and non-vampires from I don't know whether it's vampire or non-vampire, but if you have lots of data, then I can for sure like for each of these, after all each of this outcome here, in each of these kind of like sets here, like there would be mix of like vampires and non-vampires. Basically after each of the tests, there's none of the tests will be conclusive, right?
So I mean that still there's a question in the shadow. Meanwhile, for the garlic, it's a more.
Yeah, I mean like in the sense that, for example, if I have like lots of data here, very likely like this shadow maybe will become, maybe I instead of like only have 8 data, I have like 80 of them or something like that. If 80 of them, maybe I have 9 positive now.
Yeah. 18, 9 positive.
Maybe I have like 7 positive
7 positive.
and like 1 negative here, right? And then maybe I have this here is like, oh wait, did I say 80? Yeah, I say 80. Maybe then let me put 9 positive and 1 negative here.
Yes. 9 negative.
And this is a 30, let's see, 28 negative and then 2 positive here, let's say. And then here maybe like 20 negative and 20 positive here, let's say. So in that case, like how do I estimate the so-called accuracy?
The accuracy by sum of the positive, all of them. No, that's positive. That will be confusing. That way. Because that will be share the information. I mean that. Maybe we can calculate the ratio for each of the step. Calculate ratio.
Yeah, you may. So I guess one way you may do, maybe for this one, you say you have like 90% of accuracy. Maybe this is a this is you have like 50%, maybe, let's say, and this has a maybe this is about 28 over 30%, let's say, and then you weight the sum them together to get the accuracy. But I mean like this thing is a little bit ad hoc if you do it this way. I should say that this is not related to this class, and also like it's a little bit does not have a theoretical basis here. Instead, actually, we can look at like what we studied like earlier, right? So this is the shadow. That's a shadow. I call this as a random variable S here. So let's say whether it's vampire is a random variable V here, and garlic is a random variable G here. Then from what we learned earlier, like we can just look at, for example, HV given S and HV given G and so on, right? So what's the conditional entropy, knowing that S, like, and what's the remaining? Oh, wait a sec. I mean, what's the remaining uncertainty of V knowing S, right? So what I mean is like, if this one is equal to 0, then it will be a perfect test, right?
Yeah, that's perfect test.
We want to look for basically like this, like maybe I have several tests here, HS V given S, HV given G, HV given, let's say, C here for this guy here, HV given S, A here. And we want to look for the one that is as small as possible, right? And let's say if this is the smallest one, then we'll just start with that test, right? Now then, like with that test here, like how to pick the next one, we can simply compute like HV given S and also like each of them X, SMG, HV, SMC, and HV, SMA, and so on. Now again, you pick the one is the minimum, and then use that as the second test.
Oh,
Yeah.
that's right.
Then you can do it like sequentially. Then to consider the order.
So that's first step is to find the minimum one, and after that the next.
Yes.
Find
Yes. And for example, like if you think about is HV given S in this case, so HV given S will be like this will be like P S equal to N times HV given S equal to N plus P S equal to Y, HV given S equal to Y plus P S equal to question mark plus HV given S equal to question mark, right? And if you approximate that, let's say PS equal to N will be approximately 1/8, right? And this will be like 3/8, and this is like 4/8, right?
Yeah.
And what is actually given S equal to N?
S given N. P compare S given N. No. It's not 1. It's 1/8. It's only 1. No. And then we count here. It's 1.
No. N is here. N is here.
Yeah.
How about
What
HV
is-
given S equal to Y?
What is N? N is no.
No. N is no. Here.
Yeah. There is 1 actually. Shadow. There is 1 no over there. That's right.
Mm-hmm.
And then vampire is 1. Yes. So it means that from the sample 1 there is 1 vampire. Yes. So the entropy will be the probability will be 1.
Yeah.
Yeah.
So when the probability is 1, what's the entropy?
What is entropy? The probability 1. 0.
Yeah, that one is 0, right? That would be, probability 1 would be deterministic, right? It would be 0. And this one would be the same, right?
Yeah.
Because like probability is 1, like it's always is negative, so it's like also equal to 0.
Mm.
And for this guy here, you have 1/2, right? It's like,
Yeah. 1.
it's like probability, like half is like, actually it's just equal to 1, right?
Equal to 1.
Yeah, because it's
Because one half.
one half. It's like,
Mm.
so therefore like actually HV given S turns out is equal to 1/2. It's just 1/2, something like that. And you can evaluate all of this, and then by the way, let's see. Actually, if we evaluate that, it turns out this will be equal to 0.61, and this one is 0.69, and this is 0.94. So therefore, we should start with the start with the shadow test.
Oh, okay.
Yeah.
That's right. And then we find the minimum there.
Yeah.
What we should find the minimum.
Oh. So V given S is what's the uncertainty, remaining uncertainty of V given that things, right? So, and we want the remaining uncertainty as small as possible.
Oh yeah, that's right.
And also, by the way, you can also think of this HV, this minimizing HV given S is exactly the same of maximizing IVS. Or because IVS is equal to HV minus HV given S, right? So therefore, you're looking for the minimum conditional entropy given the test, but it's also the same as trying to maximize
the information.
mutual information between let's see, yeah. This is G, so basically we see which of the pair will have highest mutual information, and again supposing this term supposing should be after the computation should have the highest mutual information. Therefore, we should pick this test, the shadow test first, and
so the mutual information there is something like we want to get maximized.
yes, it will be the same, because this is equal to H V minus H V given C, right?
Yes.
So H V minus H given C and H V minus H given A. So minimizing these terms here will be equal to maximizing these terms here.
Maximizing the mutual entropy means that we want to know the biggest information, the intersection in between X and Y.
Yes,
E and S. The biggest one, because in the Venn diagram, we saw that the intersection in between V and S, it's I mutual entropy. So the biggest one that it means that if we get something like this parallel, something like this one and this one, that's the biggest one.
Yes,
That's
that
right.
will be most overlap. Yes,
Most
your
overlap,
yes,
yeah.
yes.
Yeah,
Your
most
HV
overlap.
is here, yes, and HV given S is this one, right?
Yeah.
So you have different. Basically, what you have is maybe I can draw like that. You have HV, right? HV is fixed here. So you have different cases. For example, this one is this here is IVS, right? And then maybe I have the other guy here is this is IVG, let's say. I want to maximize this, find the one share most mutual information, but that will be equivalent of minimizing the remaining one, right?
Yeah, that's right.
Yeah.
It's good.
Yes. So and this is just a tree algorithm. And by the way, since we are here, let's also mention some potential extension is people can have so-called random forest, right? What it does is event trees, I mean, basically it's just like you have like lots of data here. Instead of like just design one tree, what we can do is like we can partition the data into multiple pieces. For example, like if I have like 1,000 data points here, I can have like the first 100 points I train one tree, and then the second 100 points train other trees, and so on. Then we will have multiple trees, and then I will just like make the decision by like combining different decisions together. Maybe take a majority vote. So for example, like if we train a tree that as we go through the tree to make one decision that okay, that maybe we train 10 trees there, and the first one say is a vampire, second one say is vampire, and so on and so forth, and 8 of them say it's vampire, 2 of them say it's not vampire. So then we take the majority vote and we just say it's a vampire.
But the decision makers should be independent to each other. Because if there is correlation, that will not give whether that's right or not.
Actually, yeah, the task better. I mean, the better to be independent, but in practice it won't be, right? Because after training, I don't believe it's independent. But yeah, it's true. Like it's better to be independent. But yeah, the test I don't think it will actually after the training, because the data is like all drawn from the same kind of distribution, right?
Yeah.
And then so that data themselves will be kind of correlated to one another, and using this correlated data to train models, those models will be correlated as well. Yeah, ideally, like you want to have independent models. I kind of agree with that. But that's it. Like that is the random forest. It's actually very simple. So you just split the data, and then like yeah, maybe they have some tiny bit details in terms of implementation, but the fundamental idea is very simple. So yeah, okay. Any questions here? Oh, okay. Actually, only 3 minutes left. I guess I probably will just stop here then. So any. So yeah. So I guess yeah, okay. I'll talk to you guys next week then. Yeah, and most likely I will use Zoom again like for this, and then I will just, and I will also video tape the lecture. So if you guys have questions, can just go back to look at that, and then just send me emails if you have questions.